Okay.
Okay.
Okay, and clicker. Thanks.
So our next speaker is Shayan, speaking about time-space trade-offs for learning finite functions.
Thanks for the introduction. Hi everyone, I'm Xin from University of Washington. This is a joint work with Beame and Shayan of Gharan. Let me start with the background. So we are interested in supervised learning of finite functions. To be specific, we are given a concept class C of functions that map from the domain X to the range Y. Here, the domain X is finite, so we only care about finite functions. And the size of the range Y can be greater than 2, so we allow more than binary outputs. We are also given evaluations for some unknown function f on uniform random inputs. Here, we have a uniform prior knowledge on the concept class C. So at the beginning, we don't have any preference for the function f. And all the evaluations, they are correct. There are two learning tasks in this model. The first one is identification. That is, we want to find the unknown function f with a non-negligible success probability. Here, the randomness is over the choice of the function f and the choice of the uniform random inputs. Another task is prediction. That is, we want to predict the value of f of x for uniform input x. Here, we also require a non-negligible advantage over random guess. So the interesting problem here is proposed by Shamir and Steinhardt et al. Is what are the resources we need for those learning tasks? Like how many evaluations or how much the space we need for those learning tasks? Let me give some more concrete examples about the concept class C. So the first one is all the Boolean linear functions. And we can verify that in this case, the size of the domain X equals to the size of the concept class C. And the output is binary. Another example is all the Boolean majority functions. And we can also verify that here we still have the size of the domain X equals to the size of the concept class C. Now let's see a more complicated example, which is the low-degree polynomials over fp to the n. So here p is a prime and fp is a field. In this case, the size of the function c is p to the capital N, where capital N is the number of monomials of degree at most d. So when d is not too large, this capital N is roughly n over d to the d, which is much larger than n. So in this case, we have the size of the domain X is much smaller than the size of the concept class C. And we can have p different outputs. Okay, so let's focus on this case, this low-degree polynomial case, and consider what are the resources we need. There are actually two natural algorithms for the identification task. The first one is we simply remember everything. By a standard probabilistic argument, order of capital N evaluations almost surely span the whole space of the polynomials. So by storing all of them, we can recover the unknown function f. But the problem here is we have to store all of the evaluations, and it will cost a very large space. It's like log p times capital N times little n space. Here we shall interpret this as the dimension of the concept class C times the dimension of the inputs. And actually, we can reduce this space by a factor of n. So log p times capital N space is enough. In this algorithm, what I do is, at the beginning, we specify capital N inputs so that their evaluation, they can span the whole space. And we only remember the evaluation if the input is one of the special capital N ones. So that's how we reduce the space. But because the evaluations of inputs, they are coming in a uniform random way, so we have to wait for a long time, actually exponential many evaluations, until we see all of them. So we prove that essentially these two algorithms are all what we can do. So our main result is, if the size of the domain X is no more than the size of the concept class C, and the C has a property called small norm amplification, which I will explain later, then any learning algorithm for the two learning tasks must either use omega of log x times log c space, or with size of x to the omega of 1 meta evaluations. Here, the size of x is actually exponential in the input length, so this is indeed an exponential large number. And for the case of learning low-degree polynomials, they do have this small number amplification property. So we prove that any learning algorithm will have to use either omega of capital N times little n times log p member bits, or with p to the omega of n evaluations. This is essentially tight because this matches the two algorithms we mentioned before. And prior work, they are only good for Boolean linear functions. Okay, so now let me explain what this small amplification property is. So in formula, this is a little complex, so let's read as for any probability vector G on the concept class C, the 2 norm of m dot G grows slowly as a function of the 2 norm of G, where M is a matrix defined in this way. So you may be wondering, why should we care about this matrix M, or why should we care about these 2 norms? Let me give some sense for that. So the probability vector G, we shall think of them as a posteriori estimation after we see each evaluation. And the 2 norm of this vector G measures how much we know about the unknown function f. So for example, at the beginning, we have a prior knowledge, uniform prior knowledge. So the G is a uniform distribution, and the 2 norm is 1 over root of size of C. And for exact identification, this G will become a single point distribution. So the 2 norm is 1. So we can see that the larger the 2 norm is, the more we know about the unknown function f. Then what's the role of the matrix M? On very high level, this matrix M controls the rate of the increase of the 2 norm. So the 2 norm of G roughly increase in this way. So that's the reason why we should care about this property. Okay, so finally, let me talk about how we can prove this small number amplification for certain matrix M. We can express this property as this optimization program. So we want to maximize the norm square of this m dot G, and the condition is G is a probability vector, and the 2 norm of G is bounded. We want to argue that the objective value of this program is small. But this is actually a quadratic program because we have a quadratic object and a quadratic constraint. So kind of hard to bound. So what we do is actually we first relax this quadratic program to a SDP, and we work on the dual SDP. And finally, we can apply a special type of solution, a Laplacian solution to the dual SDP, so that we can have an upper bound on the original program.
Okay.
And in order to get results for polynomials, we apply bounds on the distribution of the bias distribution of the rate molar codes. And these are several related works I shall mention. So Ryan Russ in 2016 first gave the tight stem space trade-off for learning parities. And our work is built on the technique in Ryan Russ' another work in 2017. And I shall mention that in a recent work by Gharan and Tal, they prove very similar result to ours. And they are using some kind of extractor condition, which is essentially equivalent to our use of the norm amplification. But in the proof, we are using different way of applying the duality. So that's kind of the different part in the proof. And that's it. Thank you.
We have time for questions.
Yes.
Is there a sense in which these conditions are tight? Is there can you convert this small norm application into an algorithm? Like, do we know what characterizes this trade-off?
Yeah, I have mentioned that we have two. So we do have two kind of natural algorithms. So one is like using Gaussian elimination, and the other is like to use exhausting search. These are not a very fancy algorithm, but this already matches the lower bound. So
That's just for these specific problems.
yes.
But in general, you have a condition.
Okay. Oh, I see. the question is, in general, if we can interpret this algorithm as algorithms. So I think, I mean, the learning polynomial is one example, but the lower bounds given by the theorem is of the form. So the space lower bound is like we are still doing something like Gaussian elimination, and the other exponential exponential time lower bound is roughly like the exhausting search. So so that's I mean, it's not a problem specific. It's I think this also holds in general.
Let's thank the speaker again.